Hello, everyone, and welcome to the second lecture of Inorganic Chemistry, in which we are really going to deep dive into the concept of transition metal complexes and what do they entail. Now, in this second lecture, we are going to have only two recordings. We are going to section it into two big parts, just because I think it doesn't make much logical sense to break it apart any further. And the first part is going to be a big section on formalizing coordination compounds, whereas the second part is going to focus more on what is the effect of coordination when we actually focus on the metal rather than all of the compound. We finished up the previous lecture by addressing how do we approach molecular bonding from a more realistic and holistic point of view, in which we can actually look at the whole molecular orbital to actually see where are the electrons and what the electrons can do depending on where they are. This is an excellent example in the moment we actually use, for instance, ammonia that can be then interacting with a metal. At that point, whereas the hybrid approach will address only the lone pair as perfectly equivalent to all the other hydrogen bonds, just not a bond. We know that in the molecular orbital description, this molecular orbital is special in itself, and this will be the highest possible energy, will be mostly a character of the nitrogen, and it will be the one that can go into frontier and interact with this capability. I closed with a promise that we will see then, if we were to consider a big complex that is complex in metal and ammonia, we will also see what the metal is doing. But at this point, I think we can also raise the question, why should we assume that the metal is doing something? And this is at the core of the concept of transition metal complexes in general, coordination compounds to begin with. Whereas while you dissolve table salt that you consider as an ionic compound in water, you find yourself with a solution of equimolar Na+, Cl- that conducts as an equimolar component of two ions, one positive, one negative. If you dissolve something as notorious, like copper sulfate in its hydrated form, which is this beautiful blue compound, when you dissolve it in water, first of all, the solution is not colorless, it's blue, exactly like this thing is blue. But also, it does not conduct as if it were to be a composition of two ions, double charged, either positive or negative, with the mass of copper 2+ and sulfur sulfoxide 2-. It does not do it. If you check the conductivity of the solution, so it should tell you the mobility of this thing, it will not go in the same way. It will instead behave like the coordination of water molecule around copper. And if you add ammonia to this, which is more similar to the example that we were looking at before, you notice a stark change. The color is still blue, but the shade of the blue is incredibly darker, and it shifts immediately the moment you put ammonia, when once again, it does not conduct as a single solution of separate ions. This is the reason why we know that coordination compounds are an entity in themselves and must be treated as an entity in themselves. Clearly, they do not form with everything, but they do form with an incredible amount of inorganic compound that you can find in the periodic table. So how do we conceptualize this concept of a coordination complex? You tend to need to have a metal or something that is non-metal but is doing the same stuff, but usually these things in the center are metals. They can have a variety of oxidation state. So whatever is coordinating in the center could be very highly charged, negative charge even, or even neutral. And it can be conceptualized as a Lewis acid. Whereas the thing that you put on the side is the thing that you call a ligand. It will be bound to the metal, and it can be conceptualized in this bonding as a first approximation, as a Lewis base, so something that has electrons available to interact with the other entity. And even the neutral, even the ligand can be neutral, multiply charged, completely neutral, negatively charged, stuff like that. And one thing that the ligands can also do, in this case, you have one bond per ligand. If you add different ligands, within the same ligand, you can form multiple bonds to the same central atom. This is the concept of dentation of a ligand. So now that we know that this can be done, and there are empirical evidences that recommend that you treat them as an entity of themselves, how do we tackle these molecules that clearly are different from the formalism that we could possibly use for organic molecules? These are deeply inorganic molecules, and they have an arrangement that must be reflected in the way you formalize them. And this is what we're going to do in this section. So, first question will come with how many ligands for every metal? Now, this is not something that is strictly fixed. Whereas, for instance, in a carbon, you always expect to only have 4 bond maximum, and you go with 1, 2, 3, depending on double bonding and stuff like that. The flexibility that we already stressed on in lecture 1 allows you to have multiple options for the coordination in a coordination compound. So, how many ligands per metal is the thing that gives you the coordination number. It depends on a lot of things. Not every metal is able to have all the possible coordinations. The size of the metal, the size of the ligand, the way they must interact with each other, and the way the molecular orbitals of the ligand allow it to interact will command this sequence of numbers. But in theory, you can go really high. So an easy thing would be coordination number 2. So you have 2 bonds for every metal that you're bonding. Coordination 3, instead, the metal has 3 bonds. So you can see here they're arranged to reduce the steric hindrance, but it's still 3 bonds to the central metal. 4 is the point in which you start to also have a different possible configuration that will still give you 4 bonds. 5 is something that we've also seen last week with the Berry pseudo-rotation. So 5 is usually the trigonal pyramid, but we do need to address that it could shift in certain conditions to the square pyramidal. 6, you can see here, very crowded type of structure, but this is how you get into an octahedron. And even incredibly crowded arrangements, like the 8 arrangement that requires you to go into very deep transition metals. You cannot do this with anything that is up in the 3D row and stuff like that. So addressing the coordination number is something that you do by counting how many bonds the actual metal in the center is sharing. So it doesn't matter how many bonds the ligand has, but what is he sharing with the metal? That thing gives you the coordination number. How do you name the coordination compound? Inevitably, all of these things that we addressed. So, okay, what type of metal? What is your ligand? What is the charge of your ligand? Is the complex charged or not? Must be taken into account both when you write the formula and when you try to give it a name. So the names you have also a huge brief guide from the IUPAC, which is the International Union for Fundamental and Applied Chemistry. So these are very codified rules in the same way the rules are codified for organic molecules. You write your formulas in a way that tends to put everything in a square bracket, because the square bracket is the thing that is going to tell you that the thing that you have inside is a coordination compound. Priority is usually given to anionic ligands and second to the neutral ligands. If your stuff is charged, you just address that you have a charge. If you made a salt, so there is already a counter ion to that is really specified for this type of complex, then you must declare what is the counter ion by putting the anion before or the cation after. So you can see an example of application of this. So if you have copper with 6 water molecules around it, first the metal, second the ligand. There is only one ligand this time, and this ligand is neutral. This gives you a 2+ charged complex. There is no counter ion, so you must declare the charge. Whereas in this case, when your complex ends up being negatively charged, and you can see that you still put in a square bracket because you want to address the fact that it's not an ionic compound, is a complex, you put the counter ion before because it is a cation, is not an anion. It can even be more complex, like this case in which you have the oxalate bridging the iron. And you can see that this is a case of you actually have a coordination number 6, but your oxalate can actually bond with 2 oxygens at the same time. So it's bidentate ligand, you do not bond with just one. For every oxalate, you can make 2 bonds. How do we name these things? So you must remember some of the classical names of the ligand. So for the water, we use the aqua term. So if there's 6 of them, then you have the hexa aqua copper 2. Then the chloride will be the chlorido type of bond. So it's a potassium tetrachlorido cuprate. Or in this case, you have 3 oxalic acid ligands to account for. So then it's a tris oxalato ferrate 3. Potassium goes before. Note that I put here the point group associated with all of this. So this thing is octahedral, which makes it OH in this arrangement. In this arrangement, this is a tetrahedral arrangement that actually reflects the tetrahedral symmetry, so it's TD. This one, you can see it's octahedrally arranged, but these ligands do not allow it to have the full symmetry of OH. So if you derive the point group of this complex, you end up with D3. Please make sure to reassess all of the point groups in all of the examples as we go across. Here for your reference, I have a list of the ligands. You can also find it in your book. Some of these are things that you clearly immediately remember, like the carbonate ion, all of the halides and stuff like that. Other is worth putting a bit into memory because they are going to show up a lot. And it is useful to remember that you can have multiple bonds for every ligand and things like that. In the same way, you want to remember what a methyl is and what xylene is and what we mean with toluene or a phenol. These are standard names that is useful to remember. So these are here for your reference. So you can use them also in your exercise, and they are shortened sometimes because they can be very complex. So you might find references in the literature to something that has CP, DPPE. This is the typical thing that if you want to be able to read the paper, you need to recognize that even if you don't remember the acronym, this thing is clearly the acronym of a ligand. So these are here for your reference. And the other thing I wanted to address is the fact that now we know how to arrange them in space. They are arranged in space depending on the possible geometries that they can have with a certain coordination number. This doesn't make them immune to the presence of isomers. And we already addressed the possibility of different geometries, so they could actually change shape, but even within the same geometry, depending on what type of ligands they have, they might show the same type of isomerism that you could have in organic molecule. So in the same way, in an organic molecule, you know that the stereoisomer could have some geometric isomers in which the actual location of a substituents gives you a cis version when the two substituents are together on one side, or a trans when they are opposite side. You could also have this in the metal complexes. Likewise, some metal complexes are optically active. So they will be chiral because the arrangement makes them chiral. What do we mean with chiral? We mean that if we reflect our molecule and we rotate it under 80 degrees, it will not overlap again with what you made at the beginning. So it's something that you cannot reflect in itself. This, by the way, is something that you can check because it's going to be easier to figure out if your molecule is chiral depending on the point group that you derive. But you can have chirality and you can have geometrical isomerism. These are labeled in certain ways in the transition metal complexes. So in systems with coordination 4, your option is usually to have cis or trans type of geometry. So these are always geometrical isomers. And you can see what we mean here with cis or trans. So when we put the 4 ligands, so if you have 2 different ligands for a 4 coordination, then you have multiple options of where this thing could be placed. Right? So if you put them side by side to each other, then they will be cis. If you put them opposite to each other, then they will be trans. And this is something that you must declare because it is not inherently obvious when you say ligand 1, 2, ligand 2, 2. If you don't tell me how they are arranged, the molecule could be different. Likewise, it could be that you have 3 substituents, actually, but 2 of them are equal. And at that point, you still have to declare how are they arranged. If there were to be 4 substituents, there could only be 1 configuration. So at that point, you will not have the possibility of an isomer. Same if you were to have 3. There is no way to clarify where something goes. In a system with coordination 6, you have even more options. But given that cis and trans is a very precise way to address something, cis and trans, in the case of a 6 coordinated system, is used when you have 2 substituents that are the same and you want to address where they are. So cis when they're side by side, trans when they're opposite to each other. But in a 6 coordinated system, you also have the option of having 3 substituents that are the same. So 3 and 3, or 3 are the same, everything else is different. These are still an option. At that point, you use the notation that takes into account that this is 3-dimensional geometry. So it's the notation of mer and fac. So mer is the shortening from meridial. So it's on an axis. So they go together on the same line. You can see here it's horizontal. Even if you were to put them like that, it would be symmetrically equivalent. So you must have a straight sequence of this thing going in the same direction. So this is what we mean with meridial. So this arrangement is different from the fac, which is the facial, in which you put all of your ligands on one of the faces of your geometrical figure. So in this case, it's a face of a notahedron. So since the face of a notahedron is this triangle thing, then if your things are arranged on the face, then it's a fac isomer. So some examples of stuff that do things like this. So for instance, if you do cobalt, but 2 chlorides and everything else is an amine type of ligand, then you can decide if the chloride are cis or trans. These 2 complexes are different from each other. If you made one, you didn't make the other, and this must be declared. Then instead, if you have 3 chloride and 3 amine group, then you end up having with the possibility of configuration fac and configuration mer. Once again, not the same molecule. They are named differently and you arrange them differently because they could have also different properties. These are some examples of stuff that has the mer, and note how mer and cis could be used in sequence because you must be able to declare the sequence, right? So it could be that you need to address that some things are cis from each other, like here you have these groups that are cis from each other. But when you consider the other group, then these are mer of each other. So you must have the sequence that tells you the 3 ligands are in mer configuration, the 2 ligands are in cis trans. You need to account for all of this. Once again, this is also explained in really detailed length with a lot of examples in the guide. Please make sure for your own exercise to try to derive the point group of all of the molecules that I'm showing you, because these are very common and it will be useful if you know, and it's very useful practice in general to be able to handle them without getting confused with the crowdiness around the central atom. The other option that can be sometimes a bit complex in metal complexes is the idea that you can have optical isomers. So again, you have this difference of symmetry that doesn't make the molecule the same if you reflect it across a mirror plane. So, for instance, if you have something with this configuration with a bidentate ligand like this configuration which everything is faced out is the same as the one where everything is faced in, because these two things can be interchanged just with you mirroring them around. So it cannot be the same thing. So it cannot be different, sorry. These are the same. If instead, by arrangement of the molecule, you have 2 of these things out and 2 in, then these 2 things are not the same. And this molecule is chiral and can have enantiomers. So this one is an option. The different chirality, so the one that will bend polarized light in a different direction, would be this. So with the different one that are out and this one that are in. So these are all the options that you can have. Some of these are optically active, others are not. Another example would be this thing. So these 2 things are optical isomers. And you can see here, there is also the example of why do we mean they're optical isomers? Because this one is not the same as the other one. And this is usually easily triggered by the presence of bidentate ligands, because you have this geometrically constrained arrangement that must be respected in the space. Speaking of arrangements and projection and constraint in space, a very specific approach to chiral molecule in transition metal complexes is usually addressed with the lambda and delta type of isomers. So what do we mean with lambda and delta? It means where do you put these things? And this can be a bit complex on the point that they need to be looked in projection. So delta means if you project your octahedron through the face, the one that we say is a triangle, then you're going to have this staggered triangle. So you're going to see the tip of the other one that is behind. But with the fact that your bridging ligand is bridging these 2 points, if you go in this direction, you end up having the delta type of enantiomer. But this enantiomer is not the same as if you were to go in the opposite direction. So you can see if you start from considering this one, are you going this way or are you going this way? These things are clockwise, anti-clockwise to each other. So if you go clockwise, you consider the lambda. If you go anti-clockwise, you consider the delta. These can be very complex to arrange sometimes, but they are one of the most intriguing features of enantiomers and chirality in metal complexes. And you can see the type of complexity that they can give to the chirality that could not be achieved without this thing of coordination around the metal center. Once again, here you can also notice that you have a symmetry associated with all of them, but not all of them have a different symmetry. A lot of these arrangements are actually the same symmetry. So the ones that are highlighted end up being the one that can be repeated. Now, we mentioned before, like, oh, you can have something charged, you can have different oxidation states. How do you get the oxidation state from a transition metal complex? So you must have it arranged in space. You must know what is going on. So either it's provided to you or you arrange it in space, and then you figure out what could be going on. So if you are provided with a formula, right? So for instance, in this case, you have a cobalt, hexaamino, right? So an hexaamino cobalt something, right? And it is given to you that this has a 3+ charge, right? So, and sometimes it comes with counter ions to balance the charge, right? So the amino ligand is neutral in itself. You can have this NH3, it's fine. So all of this are not bringing any charge onto the metal. The complex is charged 3+. So inevitably, since this is 0, it is the metal that is bringing the 3+ charge. What do we do with the 3+ charge? Well, if we have our electron configuration of the neutral cobalt, then you must reduce this amount of electrons so that you can actually go to a 3+ charge. This means that cobalt 3+ is a 3d6 type of metal. Different thing with the trigonal bipyramid option here. Once again, this complex has something around, but in this case, the complex is neutral, right? The CO ligands that you have are also neutral, right? So if these are not bringing any charge and the complex in itself doesn't have any charge, then by default, you must have the same electron configuration that you will have in the standard form that you find in the periodic table. You didn't lose any electron, you didn't gain any electron, then you have a 3d6 for S2. Instead, if we look at this octahedral arrangement here, then you have a sequence of Chino ligand. All of these things bring a -1 charge. So if you have 6 of this, then this gives you a charge of -6. The complex in itself, when it's provided to you, is 3- charged. So what is happening to make sure that the overall complex is triple negatively charged, but you know that your ligand are positively charged, then you must have some excess negative charge of the ligand, but the metal must be counterbalancing some of this. This means that if you want to have a total of this, but this is what you start with, then you must get a +3 charge of the metal. If we look at the electron configuration of iron, then you subtract electrons until you get to a 3+, and then iron 3+ is a 3d5 type of metal. If we look at this option here, in which we have this sequence of acetylacetonate type of ligands, these things are bidentate. So they bond 2 times and is single negatively charged as the ligand. Right? So it doesn't matter it's bonding 2 times, it's single negatively charged. You have 3 of them, so this thing should be -3 as a charge. But the formula is telling you the overall complex is neutral. If the overall complex is neutral, then clearly you're balancing off the charge brought by the ligand with the charge brought by the metal, which means you have manganese 3+. If we look at the configuration of manganese in elemental state from the periodic table, then we subtract 3 electrons to have it triple charge, and then we know that manganese 3+ in this complex will end up having the 3d4 type of oxidation state and type of electron configuration. So this is the type of derivation that you need to do every time you try to figure out what is going on with my ligand. But either the drawing is provided to you, the formula is declared to you, the charge is declared to you, or you are asked to arrange something with a metal in a certain state with this type of ligands. What is the result? One way or another, you must know some information to be able to figure something out, which also means it is fundamentally incorrect to forget a charge if your complex is supposed to have a charge. So asking to arrange iron 3 plus with 6 Chino ligands would require either a counter ion or a minus negative charge from the in the drawing. Otherwise, the drawing is incorrect, that this complex is not neutral, and so on and so forth. Once again, do yourself a favor and use all of these examples as the exercise for point group derivation and maybe naming convention derivation. Now, we arranged all of these things claiming that, okay, these are complexes. We could do this on a point of trust. If you give it to me, I will trust you that this is fine. But notoriously, a molecule being fine doesn't mean that the molecule is necessarily stable. It could be fine on a very short period of time, or it could also be incredibly reactive. The thermodynamic stability of metal complexes passes through what we call the conceptual expansion of the 8 electron rule, which is the 18 electron rule, or 36, 54, or equivalent noble gas configuration type of rule. So you must count more electrons, but the idea that a complex will be stable still comes down to the same conceptually appealing concept, which is it must have achieved a nice balanced state of arrangement, because if it hadn't, then it would not be stable. So it could mean that some complexes are not actually in their best possible form. They might like more ligands, they might like less ligands. This is going to be relevant for when we go into reactivity and applications later in the course. So when you are presented with a complex, you might ask yourself, okay, is this stable, right? So you can do this with the effective atomic number type of calculation or with the 18 electron rule. The only difference is if you're only checking the valence electron, because the 18 electron rule is 18 valence electron rule, or if you add all of the electrons, so you actually use the atomic number of the metal to then add everything else. So if we go back into our pentacarbonyl iron that now we know is pentacarbonyl iron 0, because this thing is not charged, then we know that we have a 0. This doesn't have to counterbalance anything. Iron, you got the 26 plus 5 of this. You end up with 36 valence electron, or equivalent count 18 electron rule, right? So this brings 2, you end up with 18. If we go to the hexammine cobalt 3, as we derived before, we need to rebalance this stuff once again. So this thing has the lone pair over here. You have 6 of those. Cobalt is right next to iron, it's number 27, and now your complex is charged, so you need to rebalance the count because of the charge, which brings you to 36, or just equivalently, using only the valence electron, you end up with 18 electrons. So this complex is stable, this complex is stable. With the manganese 3 acetylacetonate, right? This thing brings you slightly lower, like it brings you to 34 total count or 16, right? Please notice that the stability sometimes is a bit dependent on where are you in the periodic table, right? Because you might be happier in the same way there are some elements that can violate the octet rule. there are some complexes that will be stable even with a slightly lower number of electrons from the 18 electron rule. So usually if you are in the middle or towards like middle point of the transition metal block, then you obey for sure the 18 electron rule, unless something is up. Early transition metals, so group 3 to 5, something like that, they will tend to have a slightly lower electron count. So it is common to find 16 electron or less sometimes. So group 6, 7, 8, 99% of the time you're going to find them in 18 electron. Group 9 or 11, once again, they might like to go lower. So you start to have a sweet spot. Remember that the only thing that can happen if you find a complex with less than 16 electrons or something like that, or less than 18 electrons, something like that, is that it might be stable in that configuration, but the thing that this is telling you is that potentially you could rearrange the coordination in the right conditions to achieve the 18 electron rule. So it might like it in certain conditions, then you put it in another condition and it will rearrange the whole coordination and the whole like amount of ligands, what type of ligands, to actually achieve the 18 electron rule. But this is something that we're going to discuss more in length in the moment we actually talk about the reactivity, because this is an effect of reactivity. Now we know at this point all the points that we need to formalize our metal complexes. We know how to write their formulas. We know how to name them. We know how they coordinate. We know what's the oxidation state of the central atom and how to derive it. And we know how to assess if they are stable and what are the boundaries of this assessment of the stability. This allows us to move to the next spot, which will be extra bits and pieces on the actual things that go on with the transition metals.